Hello, this is Darla Jones. Um, I wanted to talk to you about Chapter 5, networking cable networking. Sorry, I'm doing this again. I keep having to move it because I'm trying to put a PowerPoint in here. So I apologize. This is about the third time. But I wanted to get this in. Anyway, I wanted to talk about Chapter 5. Have you seen this before? Where you're looking at and is this you? Maybe even. We have lots of cables nowadays. Lots of them. Even though we've gone to wireless, there's still plenty of cables out there, and cable management does matter. This could, oh, wait. Okay, this could also be what you're looking at. Is this the mess that you look at? Is this at home where it's behind your TV? Is this at work where you're having these issues? And do you think these cables are all healthy and working perfectly? Something to think about is cable management. Okay, now is this you? Are you the one who's running over your cables with your chair? Are you the one who's got your power charging and you're doing the same thing? Are you using protectors to protect your cabling and here where you can drive over it? What steps are you taking? Okay, within this I want to make sure you understand some concepts. One of them is simplex, half duplex, and duplex. And it's discussed in your text, but I just want to make it clear. Okay, simplex is basically a transmitter to a receiver, just one direction, much like a megaphone. You are speaking through it, it's going outward, nothing's coming back. It's just a simplex. The OR transmission is half duplex because I can transmit this way or I can transmit this way to the receiver. So one or the other, but they can't occur at the same time. And that's like walkie-talkies as an example. When you talk into them, the other person cannot talk because you got the button down and you're talking. So it's an OR. Now what we usually use on data networks and the telephone and things like that is an AND. So not an OR, but an AND. You can transmit this direction at the same time as you are transmitting this direction. So that's the difference between simplex, half duplex, and duplex. This example of a garage with a remote would be what type? Think about it. It should be simplex. It's a remote signal to open the garage door. Okay, I created this several years ago to help put together the difference between analog and digital signaling. The idea is computers send data. Okay, there's two signaling types, and one would be digital, the other is analog. Typically, our telephones are on analog and certain things like that, and other things the computer really likes digital, but there's two signaling types. Then they both use electrical current pressure and they're both directly proportional to voltage, so they're same here, but the actual signal varies. So on analog, which is going to be, and I'll show you an analog wave, it varies. It's up and down and all around, whereas a digital signal is zeros and ones. We use these for different reasons. Let's start with the simpler one, which is digital. We use this over copper. We can use it over fiber optic as light pulses, and we can use it over electromagnetic waves in the air. So zeros and ones, and that's digital data. Analog's a little trickier because we have the signal varies, and it can vary in amplitude, it can vary in frequency, which that's the strength, the frequency of the number of cycles per time per second in hertz, and then wavelength, peak distance, and also phase, the wave process. So analog varies considerably more, but it puts together how you can compare these two types of signals. Now here's an example of an analog signal. First of all, you can see here's the amplitude. It could go up to 5 volts as in this example. If it went down here, it could be negative 5 volts, like as in here. And a wavelength would be from here to here to here. because, well, that's a wave, okay? And then, so that length would be a 1, that's one wavelength, and then a second one would end here, and a third one would end here. There's also, so that's a wave, and let me keep going, there we go. Frequency, so how frequent is this? So analog signals can also vary in frequency. Thus, 1, 2, 3, 4, but if I went faster, what if I had them going just to here, coming here, and I'm coming up at 75? So I could make it much more quick, much likely to be much more fast than, or slow it down. That's frequency. Whew. I hate doing this late at night. Okay, the wavelength I just showed you. So that's the point where it starts, and it can go from, you can go from peak to peak to peak, but basically that's what you can do for frequency. But for the wavelength, it's an entire wave is ended in one component, 1 second in this example. Okay, the phase, which was one of those that I showed you, is where this wavelength starts and it's going along, and you'll notice it's on a 90, it's actually a 90-degree phase difference because this one started 90 degrees after this one, but they're the same exact wave, but they're just in a different phase. So that's another way that you can vary the transmission. I also forgot to tell you that frequency and well, I'll worry about that later. When you look back at that image, there's an inverse relationship between two of them. And I have posted that image in the actual module. Okay, digital signaling. There's something you also need to know about is that digital signaling, amplitude would be a 0 or 1. It's on or it's off. So analog signaling is considerably different than digital. Positive voltage is on, 0 voltage is off. You can also count placeholders, and we know that a component of 8 bits is a byte, but when you say bit positions on these types of things, if it's on or if it's off, there's also a bit position. There's a 0, 1, 2, 3, 4, 5, 6, 7. Those are the bit positions. And then these are the values of the bit, which you're used to looking at. If you look, in the bit positions, we have digital numbers that represent each one of these components. So anyway, you're going to have to start looking at some of the placeholders because that's going to matter with cabling also. Thus, here's cable pinouts. All right, when you do the cabling, well, we're not going to do it in class, unfortunately. I really like doing it in class. The pin numbers are very important because you've got a pin number here, here, and they go this way. This is assuming, and I usually show a picture, but when the picture is downward here, the clip is on the back. So you're holding it, and the clip is on the bottom. And the reason this matters is you've got two different TIA, EIA 568 standards. You have the A and the B. Typically, A is used more for military and government, and pretty much commercial is more the B. So you need to be familiar with both, but likely B would be the one that they would test you on. And if you were to make patch cables with me, we would be making Bs. Now, this is important as the color, because in the first one, you've got the orange striped, orange, green striped, blue, blue striped, green, brown striped, brown. You would need to know those colors in order. So, some things to think about. The A is not the same. It switches the green and the orange effectively. But take a look at it and be aware of it. Multiplexing. All right, muxing and demuxing. The whole intent of multiplexing is to allow several signals to travel simultaneously over one medium. So when we combine the channels, we mux, and when we pull them back apart, we demux. Your book does talk about these, but without these images, it might be harder to understand. Basically, time division multiplexing divides the signal into multiple time intervals. So we've got 3 signals we want to put together, and we're going to give them all a time slot, but all the time slots are equal. So we're going to give A a time slot, then we're going to give B a time slot, and then C can have a time slot. So as they're putting these together, and this is where we mux them first. This way we go mux, the other way we'll be demuxing, but and then the pattern repeats. So effectively, it can transmit during its time, each one, and this would be time division multiplexing. Now there's one problem with this is what if, and you can see that, well, this one might have more need, or this one might have more need, but they agree they're going to each take their piece. But what if B decides, well, I don't feel like transmitting today? Well, then that means you're losing this because it's still looking for B. So basically, if somebody's not using their part when you do time division, it doesn't go to somebody else, it just gets lost. So that's a disadvantage. Okay, statistical multiplexing. This one kind of helps because the transmitter assigns slots to the nodes and by priorities and needs. So this way, it's more efficient than the time domain was. Here, A only needs a little bit, B needs a whole lot, and C needs about medium. So now, okay, B gets some, A gets a little, and C gets some. Then it keeps repeating in the same way. When it's muxed like this, the signal's being sent, so it's being sent, and then when it gets over here, it gets demuxed, and it returns back to the form that we're looking at here. All right, that's statistical. Frequency division multiplexing. So now we're looking at an analog signal, and each one is unique, but this is a different signal than this one because analog is in waves and the waves aren't the same. This one has a higher frequency, this one has a lower frequency, obviously, because there's less waves. We want to send them all together, so we mux them, put them all together, they go across together. When they're done, they become demuxed and return to their original status. This way they can be sent as one communication, a unique band for the communication, and not be interfered with during the transmission time. And then there's also wavelength division multiplexing. So same thing here, but this one's different because it's going to have, look at how many wavelengths we have, and it's a division. And this is one copper optic connection carries multiple light signals simultaneously. Maybe. All right, transmission flaws can occur. One of them is attenuation. If you have a problem and a flaw, attenuation is basically when the strength of your signal starts to degrade. There's two ways mainly that we boost things, and I wanted you to know the difference between these two because the boosters are, amplifiers are used for analog signals. And then, I really should do these earlier, I'm sorry. Amplifiers are done for analog signals, but the problem is they can degrade more when they get amplified if you have a transmission flaw. A repeater works with digital, so it regenerates the digital signal and it won't accumulate any damage. Here's a perfect example of this, and I like this image because it makes sense. So the first one's an analog signal, you can tell that already. It's looking normal, but now it's incurred some noise. Well, the amplifier's there to hopefully increase the signal because it's going to be lost in a while just due to attenuation. And so when the noise occurs, the problem with the amplifiers is suddenly when the noise occurs, you notice this beautiful little wave that was structured a certain way keeps getting, okay, so it's already, now we've got damage, but now the amplifier will make it even worse. It will amplify the error. And so that's a difficult situation to deal with transmission flaws on analog. It's just trying to deal, it should be able to just send the signal on in assuming it's not